Welcome back, everyone. I hope everyone had a nice cup of coffee and is awake so that someone can ask me some questions afterwards. Okay, so starting with my talk today, I'm going to talk about the influence of SOP in TADF OLEDs. Both of these topics you have heard about recently. So SOP was just discussed by Professor Brutting, and TADFs were just discussed by Andy Mockman in his talk. So I'm just going to go ahead from there. So I'll just give you a quick reminder of what SOP is, then how we measure it, and the effects that it can have in a TADF OLEDs. And also we'll look further what we can do with these things. So what is SOP? Again, it is the orientation of dipoles in a material which can lead to polarization. And this polarization can lead to charge formation inside in the material, where you can measure it as an electric field. And I'm going to talk about it as the lambda parameter here, and the degree of alignment, which will be the maximum possible alignment of dipoles in a molecule. So the alignment of the permanent dipole moments, which is the PDM, in a material causes spontaneous orientation polarization, or SOP. And the term giant surface potential, or GSP, is used to resolve the SOP. So here we have two materials. On the left, we have DMAC-TRZ, which is a commonly used TADF emitter, as we just saw in Andy's talk. And on the right-hand side, we have BCPO. It is a polar host material, which is commonly used for TADF OLEDs. On the right-hand side, you can see that this graph, which denotes the GSP slope, and these values for these materials have been measured using Kelvin probe. So here we can see that for BCPO, we have a really high slope and a value of 161.2 millivolt per nanometer, whereas for DMAC-TRZ, we have a value of -10, which means BCPO is highly polar, whereas DMAC-TRZ is non-polar in nature. Here we also define our lambda parameter, which is GSP over PDM and multiplied by 1 over 1 minus concentration. And for these materials, as you can see, that for BCPO, we have a value of 46.6, whereas for DMAC-TRZ, we have a value of -5. Okay, so what it is exactly? SOP can lead to accumulation of holes at the interface. So you have two-layer devices. Here you have layer 1, which is generally a non-polar layer, and a layer 2, which is a polar layer. And due to SOP, we can have an accumulation of charges on the interface between these two layers. And this electric field and accumulated charges can result in quenching in an OLED. Also, these accumulated charges can cause a shift in the EL spectrum of the devices. Moving on to how we measure these SOP. First of all, I would just like to tell you the materials that we will be looking in my presentation here. So on the left-hand side, on top, we have NPB, which is a non-polar hole transport material with no PDM. On the bottom here, on the left, we have DMAC-TRZ, which has a PDM but is non-polar, as we have just seen in my previous slides. And over here in the middle section, we have a bunch of polar host materials, which is BCPO, OXD7, and MCB-PCN. And on the right-hand side, this will be the basic device structure that we use to determine the SOP of the materials. So on the bottom, we have our substrate and the ITO as our anode. Then we have a non-polar layer, NPB. And then we have the host material, which we will be further doping with DMAC-TRZ to study the effects of TADF host on the polarity and the GSP of the materials. And on top, we have lithium fluoride and aluminum as our cathode. So here is the same structure that we have seen just now. And we use this formula over here to calculate the SOP of our devices. So what you see over here, this is a CF measurement, CV measurement, which is a capacitance voltage measurement. And this step over in the measurement that you see, the increase in the capacitance is used to calculate the SOP of the material. So and the shift in the step of this increase in the capacitance will tell us if our SOP increases or decreases. So if the step goes towards a higher negative voltage, that means we have an increase in the SOP. And if it goes towards a positive voltage, we see that the SOP will decrease. I will also use the term SOP and GSP in relation to each other. So sometimes I will say SOP and also GSP, but so they are the same for now. Let's just say that. Okay, so for this material called OXD7 over here, we did 4 measurements. So we had that device structure that you just saw, and then we had a neat OXD7. Then we doped it with 10, 20, and 50% DMAC-TRZ, which is a TADF emitter. And what we see over here is for neat OXT7, we had a transition in a rise in the capacitance at around -4. But as we increased the doping percentage, we saw a decrease in a shift in the transition voltage over here. But after a further doping percentage, which was after 20%, at 50%, we see that the shift is in the positive direction again. This, you can see clearly over here, that the GSP first increases as we increase the doping percentage, but after a certain doping percentage, it goes down. We also have another class of materials called BCPO. It is also a polar material, but what we see over here is a constant increase in the voltage, in the offset voltage, which suggests that with increasing doping percentage of DMAC-TRZ in this material, we see a steady drop in the GSP of this material. So with neat material, we have 163 millivolts per nanometer, whereas with 50%, the GSP almost halves itself. Okay, why do we see this different behavior for these two materials? To explain that, we first have to look at the PDM and the GSP of these two materials. So what we have over here is BCPO. It is a material with low PDM compared to OXT7, but a comparatively high GSP value. On the other hand, we have OXT7, which has a higher PDM, but a lower GSP. So what you see over here is, in case of OXT7, we see a almost steady increase in the lambda prime parameter, which is the degree of alignment, with the increasing concentration. Whereas in case of BCPO, this value remains almost constant. To explain it further with something more visual, here I have this diagram over here. So first, let's look at BCPO. So these arrows indicate the permanent dipole moment for this material. So here we have neat BCPO. And since DMAC-TRZ is nonpolar in nature, I denote it as this arrow over here. So what happens is, in case of increasing doping percentage in BCPO, we see a steady dilution of the permanent dipole moment of this material, and thus the GSP goes down consistently. Whereas in case of OXT7, the material already has a very high PDM. So with increasing DMAC percentage up to 20%, we just see that the degree of alignment slightly increases. Therefore, the GSP went up, but over a certain percentage of doping of DMAC-TRZ, we see that the dilution effects kick in, and therefore, the value for GSP for 50% OXT7 went down further. So what this means in terms of devices. So here we have a structure of a device where we had the anode as usual, and then we have a whole transport layer. Then we have our DMAC-TRZ doped host material, and then ETL and cathode. So this is the kind of stack that we used. So we used molybdenum oxide and MCVP and TCTA as our whole transport side. Then we had our DMAC-TRZ MCVPCN as our EML, and then DPEPO and TPBI as our electron transport side, with lithium fluoride and aluminum as our cathode. It is slightly complicated to see how big of a difference it makes in terms of the electrical properties of the OLED. But what we can see over here is the GSP of MCVPCN goes down consistently when doped with DMAC-TRZ. So the 10%, 20%, and 50% doping of DMAC-TRZ decreases the GSP of MCVPCN. But if we look at this JVL curve for the different devices for 10, 20, and 50% DMAC-TRZ, we see that there is a slight difference in the current density and the luminescence, but it's not very evident. Also, when we look at the EQE for these devices, we see, first of all, that the EQE increases slightly, but with higher percentage of DMAC-TRZ, it goes down. What the reason for this could be that since we are adding more DMAC-TRZ to the OLED device, we could see some accumulation of the charges because of too much DMAC-TRZ, and thus some additional quenching. Therefore, the EQE goes down. Also, on the right-hand side, we see a slight change in the EL spectrum, but this isn't too consistent, or I would say it's not that visible to see that difference between the different doping percentages for DMAC with the doping of DMAC-TRZ in MCVPCN. What we can see further is the quenching which can be caused due to the accumulation of these charges. As I said earlier, with the accumulation of charge, we can see quenching. So what we have over here is a continuous electroluminescence and photoluminescence analysis. We call it SEPA. So what we do over here, we measure our device, we bias our device under a certain voltage regime, and then we also measure the PL at the same time. And what we can see over here is that in the first regime, which is the negative regime, we see a slight decrease in the PL, not the PLQE of the device, whereas in the second regime, when we start seeing the accumulation, our accumulation because of the holes, our quenching because of the holes increases. And in the third regime, which is the turn-on regime, as soon as the electrons come in, we see a high quenching of our PL for the device. So what can we do further with these? So we saw that SOP is dependent on the degree of alignment and the PDM of the host materials. And doping TADF emitter in polar host materials can change SOP significantly. And SOP also controls the accumulated charges, which can negatively impact the performance of OLEDs, as you just saw, with the difference between the 20% and the 50% doped DMAC-TRZ devices. And quenching due to accumulated charges is significantly lower for DMAC-TRZ molecule. And with that, I would like to thank my group, and thank you for your attention.
Thank you. Thank you, organizers, for having me here. Today, I would first of all, I'm Illia Serdiuk. I work as assistant professor in the University of Gdansk. We mainly focus on the materials TADF emitters in the blue, red, and NIR range for OLEDs. But today I would like to tell you something about more examples on the rotational model, which describes the photophysics, the emitters which deviate from our classic understanding, the classic photophysical understanding of the TADF. And basically, these all emitters have donor-acceptor structure. And just to recall what the phenomena we are dealing with. So the thermally activated delayed fluorescence, we actually talk about it as applicative phenomena when we use electric excitation, electroluminescence in OLEDs, because most of our excitations rely on the triplet state. So 75 of excitation gives us triplet excitons, and we would like to transfer them to the emissive state, which in the most cases is the charge transfer state, which produces the emission. And the basic classic photophysics explain this by the allowed transition, or by Al-Sayed rules, the allowed transition from triplet to singlet, and this transition should be mediated by the different nature of the state, so we cannot transit directly from the CT triplet to CT singlet. We need a third state of different nature to have non-zero spin-orbit coupling, and then to have a more allowed transition from triplet to singlets. But lately, so we saw very nice models which explain the state-of-the-art emitters by Professor Monkman's group, Professor Adachi, Professor Bredas, and so on. But lately there are some examples which appear in the literature which question if when we go at the other examples, when we have wider range of polarities, for example, or wider ranges of energy gaps, there are some examples which question if CT-CT transition is actually not forbidden. And today, actually, I would like to focus on our results, which show this phenomena. And just a few words about the structure of the emitters. So basically, we have donor, acceptor. We can change these donors and acceptors. And the most important excited state, they have charge transfer nature. This means that they are formed by the transition from the HOMO and LUMO, which are separated spatially. And the most important parameters of these transitions is that they are highly sensitive to the polarity of the minimum. And due to the separation of HOMO and LUMO, we have very small CT-CT energy gap, but very small oscillator strengths. And that's why, as it was said before, we need, for example, hypofluorescence to use them in devices. And another important excited state has local character. This is usually the intrinsic property of donor-acceptor fragment itself, and they're less sensitive to the polarity, and they mainly depend on the fragment they are localized on. And just a few words about our research methodology, as we are trying to explain the experimental results from different materials. Basically, we are dealing with two main parameters: the energy gaps between LE-CT, delta E LE-CT, and delta E CT-CT. So these two energy gaps seem to be the most important, the singlet triplet energy gaps. And using for example, the three-state model, so it seems that we need to, for example, for the blue emitters, which we are focusing mainly on, we need to push up the energy of the LE state to make it closer to the CT singlet. And we do this, and we correlate our inter-system crossing and reverse inter-system crossing rates to see if we get an improvement. Of course, we can also tune the CT states energies, also do correlations, but this is in an ideal situation. So basically, after each modification, we need to check how each energy gap influences the gap and in the reverse inter-system crossing. And we usually calculate these rates of using different mechanisms of TADF, using Markov theory, and we also check if our applied model works for all the compounds and conditions. We do not want to get a model which explains only an artifact or just limited conditions. And our first approach was to tune the LE state energy, and we took this MAC-TZ emitter, which was discussed in detail today already. So the first idea which comes in the mind with this emitter, if we have the lowest excited state of triplet nature localized on the acceptor, we need to modify the acceptor. And we did this with introduction of some electron releasing substituents. And by this, we increase the LE energy, also increase the CT state energy, and we shift the emission to deep blue. And also for some emitters, we decrease the LE-CT energy gap. The basic question, did it help to enhance reverse inter-system crossing rate? The simple answer, no. Even though we saw the increase of the triplet energy and increase of the CT energy in our TADF transient fluorescence, transient PL experiment, and in our correlation, we also only saw that the inter-system crossing itself has a strong correlation with the energy gap of LE-CT. So by manipulating the LE energy, we can increase or reduce the rate of the inter-system crossing. But when we were trying to find the correlations with the reverse inter-system crossing and LE energy or LE-CT energy gap, we didn't see any correlation which would explain these results. But if we use the CT-CT energy gaps, so for the medium, for different media, we see that the correlations are really strong. And importantly, we could also see that the reverse inter-system crossing and the CT-CT energy gap was so important for the AQE in the devices that we also saw the correlation. We were very, very surprised because AQE it's a complex parameter, but we saw almost linear dependence here. The bad results was, of course, that our model compound was the best of this series. Any modifications which we done, so it was better, worse material than previous model compound MAC-TRZ. Yeah, it was a beta lesson, but we had to learn it. And so just to sum up this approach, show the most representative examples. For example, we have the reduction of LE-CT energy gap almost 3 times, but a slight reduction of the CT-CT energy gap provided us the decrease of reverse inter-system crossing and a drastic drop of the AQE maximum level. So the most important conclusions we had to draw from this, that in this group of materials, in the blue emitters, we saw that the LE-CT transition facilitated inter-system crossing rate, but we didn't see an increase of the reverse inter-system crossing rate. And as we need to use the weak donor-acceptor materials emitters for the blue TADF, the important conclusion that if we even minimize the LE-CT energy gap, we cannot compensate the increase of the CT-CT energy gap because we are using the weak charge transfer system. And most crucial, I think, the conclusion here is that CT-CT energy gap is extremely important for the reverse inter-system crossing rate. For me, it was a very surprising result, and I didn't understand why. And we had to, we used another approach, so we we went to solutions. And again, we used the MAC-TRZ emitter. In this experiment, it was solutions, just allochromic measurements. And as we know, in low polarity medium, we have an alignment of states when the lowest triplet state is localized on the LE triplet. And we usually can see the LE phosphorescence in hexane, in frozen solutions, or in frozen Xionex non-polar films. But when we increase the polarity, in solutions we can increase the polarity much more efficiently than in films, we can obtain the situation when the city states are isolated, so we leave behind the LE state and we increase the LE-CT energy gap, but also we should note that the energy gaps for the city between the city states are decreasing. We saw a very nice shift of the PL emission, so it covered all the range, and the most important alignment of the states and most important examples are shown here. So we have almost zero energy gap for the CT and LE, where LE is the lowest or LE is the second lowest triplet state. And in dichlorobenzene, for example, this is the situation we have one of the highest LE-CT energy gaps. And in this case, we see that the CT states are isolated. And the most impressive was the result in the most polar, in the higher the polarity, we saw the better performance of better TADF performance. And I just want to remind you that it could not be explained by the three-state TADF model. So the LE state should be close to the CT. So we need to see the maximum somewhere here. So it's a plot of reverse intersystem crossing rate constantly, its logarithm versus the CT LE energy gap. So we need to, somewhere here should be a maximum for it, but we do not see any maximum. It's just a function of the energy of the state. The lower we go with the CT state, we see the increase of the reverse intersystem crossing. When we plot it with the CT-CT experimental parameter, which is radiative rate constant, we saw the dependence of the intersystem crossing rate and reverse intersystem crossing, and it suggested that they are increasing with the decrease of the CT-CT energy gap. And at this moment, I had to just accept that the CT-CT transitions are not forbidden. It took some time. I didn't understand why, and had to understand why the constant spin-orbit coupling constant is not zero. And I think at the same time as we were working with this, and we came up with the rotation are important. The Professor Monkman's group also published a work where they explained the rotations of the donor and acceptor fragment. They are very important. And actually, we took a look on one of the first vibration in these materials. Actually, it's the rotation of donor and acceptor fragments, and we saw that the CT-CT transition actually can be very extremely efficiently enhanced by the rotation. So it comes from zero. Almost zero, I don't know which one. They're always zero in these calculations. So we go up to 0.5 reverse centimeter for the spin-orbit coupling for these materials. Also, we change the energy gaps, so we need to analyze all in the detail and to analyze all the parameters which affect the reverse intersystem crossing and intersystem crossing rates. We did the calculations and used the Marcus-Hash equation. So basically, the most important parameters are the spin-orbit coupling constant, the energy gap, of course, and another important parameter is the reorganization energy, especially when we talk about the CT-CT transition and LE-CT transition, because they have different geometries. The geometry defines the reorganization energy, how much energy a molecule had to spend to come from one geometry to another under the transition. And we correlated our experiment with the two and a sum of mechanism of this spin flip transitions. So in the case, both in the case of intersystem crossing and especially in the reverse intersystem crossing rate, we had just a perfect correlation with the CT-CT transition itself with the experiment. And at this time, we sum up that the CT-CT transition, first of all, it's rotationally enhanced. Those the rotations at the room temperature and in solutions, they enhance and they enable the transition, which is forbidden by the Seidel-Ruhl's law. And also the small reorganization energy is very important. Just to skip maybe a bit, I was looking for the ways how to accelerate the CT-CT transition, and if I understand that this is very important for the TADF. So at that time we were collaborating with the Korean group, and we studied these materials, these DPS materials, and our best material actually was also one of the blue emitters, sky blue emitters, and for a long time we could not explain why these materials, which are the best one, they are more distance from the LE, each LE state, which they were really high, they had high energies, and but these materials had the highest PLQI, the shortest DF lifetime, and also the lowest efficiency roll-off, so they were one of the best in our lab. And we developed again this model and showed that for the best CT-CT, for the best emitters, the CT-CT transition is the most responsible for the TADF, and for the weak donor-acceptor, actually we switch on to the a large portion of the LE-CT transition, but its rate, due to the large reorganization energy, its rate is much slower. So at this, we also understood that the CT-CT transition not only allowed, but it's also very important for the high performance in OLEDs, and it's because for the all rotamers, even though that's not so much of them, the emitters which are trapped in the non-equilibrium positions, they need to be converted effectively to singlet states. And in this, just a few words, we also use this CT-CT transition, and also we need to remember about these rotamers when we use, we are trying to accelerate the reverse anti-system crossing in blue materials by heavy atom effect. And if you're more interested, there's the vibrations which accelerate the CT-CT transition by bromine atoms in blue materials. If you're interested, this was published in GMCC, I think. And also not only for the blue materials and donor-acceptor, separated donor-acceptor structures, also in the more planar structures, we can also see that the CT-CT transition is also important, and the rotamer is also very important, and the alignment of the heavy atoms can be also explained by the important role of the CT-CT transition. And I hope that I convinced you that we need to analyze mainly a lot of rotamers, a lot of non-equilibrium materials, emitters, and their isomers in microscopic system, and that we need to look on all the possible ways, because actually we have a lot of evidence that this CT-CT transition is no longer forbidden. And at the end, I would like to thank all the sponsors and all my hard workers and you for your kind attention.
Thank you very much for your presentation.
Okay, great. Well, then, hello, and thank you for having me here. My name is Camilla Vael, as I was kindly introduced by Balthasar before, and I'm talking today about temperature-dependent dynamics of reversible electron traps in especially super yellow. Now, this is another topic than we were before, so no TADF or something like that. So we are focusing here now on trap states. Trap states are widely looked into because they usually have a very detrimental effect on our full devices, and especially electron traps seem to have a really major effect on the electron mobility in most of the semiconducting polymers. And this is attributed to several kinds of electron traps, and one of those, which is quite notorious, is the, where is the laser, by the way? Ah, here, okay. One of these trap states is the water and oxygen-based trap state at around 3.6 electron volts below the vacuum level. And most of the polymer usually have a LUMO which is above this level. So this is, in fact, a trap state which lies in the gap between LUMO and HOMO, and contributes to the slowing down of electrons inside those kind of polymers. Also, in the polymer I used, that is super yellow, we expect this kind of traps because we have a LUMO that is higher, and we have a difference between those kind of trap states and the LUMO of about 0.65 electron volts. Now, the reason why this is important is because during our studies, we noted that when we apply a constant current of about 10 milliamps per centimeter square in our case, we not only can observe the increase of device voltage due to hole traps, but also due to a kind of electron traps with a trap depth of about 0.65 electron volts, which suspiciously sound close to the electron trap, which usually is present in most of the polymers. And so how can we distinguish between the hole and the electron trap? Well, what we can see is that the hole trap development takes place in a very long time frame. So if you reduce the time frame to only a few minutes, and we use a rest time in between. What we can see is the development of electron traps and also the decay of electron traps. This is something curious because usually when you have degradation due to formation of traps, you don't expect to have decay of trap states. And just to see that we don't have a substantial amount of hole traps forming, this experiment took place in about the same time frame as this experiment, and we have a lower increase in device voltage. And also what we can see is a significant recovery when we rest the device and do not apply any constant current. Now the question is, okay, we know the energy of these trap states, but how many of those trap states are developing during this experiment? And it's not so easy to get from this measurement to our trap state density, because it's not directly extractable. So what we have to do is we have to apply some kind of model. And we decided to take our stack and make a very simple electric stack consisting of just the p-dot layer, the super yellow layer, and the calcium layer, and do drift diffusion simulation to get to the number we want to extract. But the thing with drift diffusion is it's usually based on constant voltage experiments or simulations and not on constant current. So in order to simulate this trap site density, we have to include an extra step, and this extra step consists of just trying to optimize the simulation to get a specific constant current, in our case this 10 milliampere per centimeter square, and this has to be done by optimizing or manually just shifting different parameters. And one thing here in particular is if you want to do this, you have to change at least 2 parameters at the same time, because if you change one parameter, which has influence on the current will either increase or decrease, so you have to take another parameter to compensate for this change in the current. And the pairs we used for these simulations is the electron and the hole mobility, or the barrier and one of the mobilities. And when we do that, we can get to our basic baseline of 10 milliampere per centimeter square. And when we reach that, we can now simultaneously increase the voltage and the amount of trap states, just to see how many trap states we need to reach a certain voltage. When we do that, we get this kind of graph, and we can get the number we are looking for, the trap site density at each voltage. Okay, so we did this kind of simulation now for all kinds of temperatures that were available for us experimentally. And here on the left-hand side, I show you an experiment where we just stress the device for 5 minutes at 10 milliampere per centimeter square at 230 Kelvin, 270, 300, and 330. And one thing that is notable is up to the temperature of 300 Kelvin, we have an increase in voltage. So the higher the temperature is, the higher the voltage increases. This is only true up to 300 Kelvin. So if we go above this, what we have is a slower increase in voltage. This is something for later. Now we can actually simulate this results, and we get the graph here in the middle, so it's quite close to what we measured. But when we take a look at the trap sites that are developing, we can see that we have a monotonously increasing number of trap sites. So the highest density of trap sites evolve at 330 Kelvin. Now, why is there the difference between 330 Kelvin being not the highest, but having the highest trap site density? Well, one of the reasons is that we can get quite close to the glass transition temperature at 330 Kelvin, and it is possible that we start to have significant changes inside the device as well. So we don't need to increase the voltage as high to have an effect from the trap side. Now, one thing that we also noted while doing the simulation is that we have quite a high dependency on the parameters we choose. So here just show you two parameter variations we've done. So on the left-hand side is the same graph I showed you before. We have here a fixed mobility ratio between electron mobility and hole mobility of 1 to 10. And we also fix the capture rate to this number to 5 times 10 to the power of minus 13 centimeter cubed per second. And in another simulation, what we do is we take the same mobility, but we calculate for each of the mobilities the associated capture rate. Now, when we do that, what we can see is that we have an increase in trap site we have to add in our simulation. That is up to a factor 5 higher than in the case where we have a constant capture rate. And this is quite a significant difference, and this already shows that we cannot pinpoint the number of our trap states directly. So just to show you the difference between those two simulations in numbers. So what we used here is the mobility for holes, which is 10 times higher than the electron mobility. And this mobility was derived by just fitting the mobility to the experimental voltages we measured in our experiment. And what we can see is that we actually have an increase of the mobility, which corresponds to an activation energy, which is exponential. So this is exactly what we expect for our device. Now, this capture rate, of course, is only for the second simulation I showed you, because in the other one it was constant. But what is important to note here is that the capture rate for holes of the electron trap is 10 times higher than the capture rate of the electron trap for electrons. This means that we have a quite efficient Schocker-Reed-Hall recombination, and this means we have very little field trap. This in effect means that the number of trap sites we have to add in our simulation to see an influence on our current is significantly higher, and this explains the difference we can see between those two simulations. Now, another question that is important is to see we have electron traps which develop slowly over time. And it takes longer than we usually would expect for electron traps to be filled. And the question is, why is it that much longer? So we are talking about a difference between 200 microseconds to about 1 second to 15 minutes. One of the theories we have is concerning this complex here. So it is consisting of 2 water molecules and oxygen molecule. And when it has electron captured, it is quite stable. These are the 3.6 electron volts we usually find. But when we remove this electron, what happens is we have a very, very unstable complex which has an energy of about 0.016 electron volts. And just as a reminder, at 300 Kelvin, we have an energy of 0.026, basically, meaning that this complex will dissociate quite fast. So in order to actually get a trap, we need to start from the components, basically meaning that we have a 4-body reaction to form a trap. And the chances of that happening at the same time is not very high, which increase the time of trap formation. This theory has to be tested thoroughly, and we started with kinetic Monte Carlo, but we haven't yet conclusive results, so and I'm running out of time, so I have to come to the conclusion. We modeled the voltage increase in our drift diffusion simulation with an increase in the number of trap density, and the density we got from the simulations corresponds to the density of trap states we would expect for this kind of trap state at 3.6 electron volt. And what we also could see is that the trap formation rate increased with increasing temperature, meaning that actually a diffusion process might be viable. And also we saw that the number of extracted traps is very dependent on the input parameters. So what we can say is maybe we have this diffusion of oxygen and water molecules as a process for the trap formation, and we need to investigate this further. And at this point, I want to thank my colleagues at Fluxim and Wei Shu for preparing the devices, and Roland Hani and Frank Nürsch for their support. Thank you.
Whole cell.
Okay, thank you. So yeah, I'm coming, as I said, from Umea University, and the result I'm going to present is done in the organic photonic and electronic group from Professor Ludwig Edman. Yeah, and you read the title. So first of all, since it's quite different from OLED, well, not that different, I'm going to present what is a light-emitting electrochemical cell, or an LEC in short. And to be quick, I'm going to say it's pretty much like an OLED. So we have an active material layer in which we have an organic semiconductor. We place between two electrodes, we bias, we get light. And since it's amorphous and so on, it has all the beauties of OLEDs, like flexibility, large area emission, emitters, organic material, so that means a rich color space, so on and so forth. But the characteristic thing of LECs is that we add the active material is a blend of an organic semiconductor and an electrolyte, meaning basically mobile ions, right? And this will it allows us to get away with a much simpler structure than OLEDs. Like, we can get away with a simple layer. And in a minute, I'm going to show why, but we can also get away with large thicknesses, means like the devices that we fabricate can be fault tolerant and then for large scale fabrication. And also, they are relatively insensitive to electrode choice. We don't need to match the work functions, and I'm going to show you in a second why. And this means that we can use air-stable electrodes, and then all these three combinations potentially can lower the fabrication costs, and this is where the LEC have a certain advantage respect to the OLED. It has other disadvantages, but I'm not here to talk about them today. So a short note on the working mechanism of LEC. As we said, we have the biased active layer between two electrodes. We have bias, and then since we have ions in it, mobile ions, these will respond to the electric field. They will accumulate in the respective electrodes, and then these uncompensated ions will create these electrical double layers that will effectively thin the injection barriers, and then we will get injections in both electrodes. As soon as we get injection, they can recombine, start forming by emission of light, but we will have another process that will continue going on, that's an electrochemical doping. So at the end, a PIN junction will develop in situ, right? Because we have electrochemically dope the whole active material, or the whole layer, right? So since this PN junction is formed in situ and dynamically, normally in LEC's field, we show the transients, and this is how a transient of an LEC looks like. We have an increasing luminance because more and more charges are injected, and we have a decreasing voltage. This is in constant current. We have a decreasing voltage in time because first we have the injection layers, the electrical double layer formation that allows the injection, and then we electrochemically dope the material. It means it gets more conductive, so the voltage drops down in this case. But what I'm going to talk today is about this emission, this emissive PN junction, or I'm going to call it emission zone, and about the properties of this, because a priori, we don't know where it forms, where is it formed. We don't know anything about the width, and we don't know. I'm going to show also about dipole orientation. So I'm going to talk about this emission zone. And for that, I'm going to show you how to use the weak microcavity to extract relevant information on that. So we have already seen in the previous sessions what's this microcavity, but in short, we have this layer of a certain refractive index sandwiched in between a semi-transparent electrode and a highly reflective electrode. And it emits from a certain position, and this emission is the same, the wavelength of this emission is the same order of magnitude of the cavity. So we have an optical cavity. And then where this emission takes place, it's very relevant for the device performance. First, because we will have optical constructive and destructive interference. We'll also have like total internal reflections due to have these high refractive indices, and we need to couple the light. We also don't want to be close to the electrode. We also will have a parcel effect that we've seen before. So this cavity will affect the performance. And generally, we will see that as a modulation of the luminance or the outcouple efficiency with respect to the distance from the cathode in which the emission zone is, or this. The important thing is the optical path difference, actually. Not only in the luminance, we will see also differences in the spectral shape, because we have this interference, essentially, and we also see differences in the angular dependence. And what I'm going to show is like how we can use these properties here to reverse and track where the emission zone comes from. And here I'm going to do a note on why this is important in LECs and maybe not that relevant in OLEDs, which it is, by the way. But in an OLED, you basically can set this optical path difference or the emission zone in a position of optically constructive by fabrication. You basically make essentially the electrotransport layer or whatever layer between the emission layer and the reflective cathode by fabrication. But an LEC, this distance is basically set by the thickness of the layer and where the emission zone forms. And a priori, we don't know where this emission zone forms, and it needs to be measured. And here is where this cavity kicks in. So what I'm going to show today is, my goal is just to show 4 examples, is how we, in our group, exploit this microcavity to extract relevant information of these LEC devices, and in particular, these 4 cases. So I'm going to go relatively quick on that. So first, we have studied a lot this kind of canonical LEC in which we use this super yellow. We have already seen it. It's like this PPB-based polymer with a certain ion transporter or ion solvating material and this salt, which is the one that provides the ions. And what we do is we measure the EL dependence, the angular dependence of the EL of this device. And then we use a simulation software, SETFOS, which models these the excitons as these radiating antennas and use this transfer matrix formalism to simulate the spectra, and then we ask where would the emission, we do a fitting, so where would the emission need to come from in order to have this spectra. So we do the fit, and we find that the emission in this case is in the center of the device. Just I'm going to show you how it will look if it was not centered, so that to convince that it's a good fit. So this, you see that the spectra is right, it's different. And then we decided, okay, let's try a different thing. We made a small modification on the side group of this ion solvating material, this ion transporter. In this case, from an hydroxyl group to this OC, octyl carbonate something. And we see that we measure the EL intensity. We see that already have a different spectrum. And then we do the fit. We find that is at 0.3. Now, this has certain implications on the device efficiency, but it's not for today. My key point here is that we can extract relevant information of the electronic mobility balance in the system, so this will be more balanced than that one. And in that paper, but it's not the point now, but it will show as well that now we have a way to possibly control the emission zone position and put it in when we do a mixture of these 2 ion transporters, and position the emission zone where we want, depending on the device thickness and so on, in terms of outcouple, in terms of efficiency, let's say. Now, a second example I wanted to show is, as I said, these LECs are dynamic, so we have a transient, and then this is how the transient looks like. This is the luminance, and then this is the voltage going down over time. And now we have a system where we can track this emission zone position using this cavity. So what we can do is we track the position of the emission zone over time. In this case, we see that it forms closer to the cathode, meaning that the cations are faster, and then it goes towards the center of the device. But we cannot not only do that, so we can also link this with a simulation tool. We can now link this luminance drop. It's not something electrical. It's basically due to a cavity effect, because our device is moving from an optically constructive position to a slightly more optically destructive interference. And you see that it correlates really well with the luminance. I'm showing this just to tell you that we can extract information, for instance, of the ionic mobility of the system, because in this case, depending on which electrode is the emission zone form closer, we can get ions are faster than cations, and so it is very relevant for us. To put another example, in a recent publication, it's now under review, we see that also that when we use a soft electrode, so we replace the ITO for P dot, we see actually that some ions are transferring into the P dot, diffusion, or drifting, actually. And then we see that as well in the emission zone position, because it shifts toward the soft electrode. This is an example I wanted to do. We can go to a more advanced optical modeling, and then we start, if we don't fit, until now I feel like this emission zone has a delta emission, like very, very thin, which is quite true in many LEC systems, but it's in an accuracy, so it can have a certain width. So if we want to fit that, in order to be sensitive to the width of the emission zone, we need to go to use what is called dark devices. So devices that are really in the optical minimum, and then this will allow us to obtain a certain width of this emission zone. Right? So we did that as well, and then this is just a sketch of what we obtained. We use this peak shape function in which the only fitting parameters is the position and the width of this emission zone profile. Without going too much in details, we had to include doping, because when we have this electrochemical doping, this P dope and N dope regions, we will also change the optical properties. So when we build our model, these optical properties needs to be accurate, so we need to add somehow these doping profiles. Anyway, when we do that in this device, dark device, we see that the strong shift in this emission zone, the strong luminance dependence, changes in luminance, and this is due to this emission zone shifting. And then what we want to do is like not only shift the emission zone, we see the position, we also fit the width. And in this case, we see that we have a widening of the emission zone, and we can actually correlate well with a higher voltage. It's not really appreciated here. But this also is telling a lot of information for us in these devices. And finally, a final example of what we can do with the cavity in our devices is extract information of the emitter orientation. So we've seen before in some talks, we have already seen why in OLEDs or LECs or distant devices we prefer horizontal orientation of the emitters, and that's basically because horizontal emitters will emit light in the forward direction that can be easily outcoupled, while vertical dipoles, the emitting dipoles, will basically emit in the parallel to the substrate, and this will be coupled into surface plasma SPPs modes, waveguide modes, and so on, right? So we can use the same dark device as before. And then we measure first the S-polarized spectra because it's insensitive to this orientation. And we do that because we really need an accurate snapshot of the optical structure of the device. So what we do is we fit the emission zone with a certain width, we fit with the profiles. Well, we construct the doping profiles that have different optical properties, and we extract that. And now that we have this snapshot of the LEC at the optical minimum, we can measure the p-polarized spectra, which contains information of the vertical dipoles. It's through this anisotropic coefficient, and then we do the same. We measure the p-polarization. This is the spectral radiant intensity map. So, and we do this experimental, and we do the fit. We see a good agreement, and here we can just see this plot, but summarized in this polar plot, where we have integrated over the wavelengths. And we see that the blue lines and the blue dots and the continuous black line is the fit, which gives a highly anisotropic, highly horizontal. Tells us that the dipoles only have very few vertical dipoles, and if we compare it to the isotropic fit, we see that it's really far off. So it's a good fit. And anyway, the conclusion here, is that around 96% of the dipoles are horizontally oriented. This has quite common in these PPVs, like these long chain polymers that tend to lay flat. But yeah, so this was my goal, show what we can extract, not too much into the details, but I hope I have convinced you we can use the weak microcavity to extract relevant information of LECs. Particularly, I've shown this emission zone position, also the dynamics of this emission zone. We can extract the emission zone profile as well as dipole orientation. The last one can be particularly relevant if we use LECs with the small molecules, which can actually realign, because it's in a very highly mobile environment. So it can potentially, and in the PN junction, we have a very strong field. So it could potentially reorient during the operation of the device. It's not so relevant maybe for this long polymer, let's say. Yeah, well, thank you.
Thank you very much for your nice presentation.
Yeah, thank you. Hello, everyone. I'm Xiaoying. I'm PhD student from Umea University. After the exciting presentation and discussion from my colleague, I will continue this topic about LEC. But I will only focus on few part of the application about this emission replanation. Today I will talk about this light-emitting electrochemical cell characterization with different current density.
First, let's start about the background. Usually we call it LEC is a light-emitting electrochemical cell. This is an emerging electroluminescence technology with some great advantages in the fabrication process. So, for example, it can be fabricated with low cost and less complex procedures than LED on different substrates. For example, it can be this glass substrate, or it can be this plastic, or it can be even paper or fibers. Now, in this slide, I showed about these simple structures. For our research, we usually use this sandwich structure. This active material is sandwiched between electrode, the reflective cathode, and the transparent anode. In the active material, usually we include this luminescent polymer and electrolyte. This also can be some ionic semiconductor. If we bias between these electrodes, then there will be light emission from the active layer. This is the electroluminescent process. When we bias between this electrode, first the ions will move towards the electrode. Later, there will be electric double layer near this electrode interface. This will help this electron and hole injection into this HOMO and LUMO for the electroluminescent polymers. This is the electrochemical doping process. Between these P and N-type doping regions, there will form this p-n junction. In this region, it defines the emission rule potential. We call it emission rule. Why this emission rule is important in LEC? I will show you these figures. I think maybe we are a little bit familiar about these figures. If this emission rule is different positions, then the emitted light, they can have this destructive or constructive interference. If they are destructive interference, then the emitted luminescence, it will be pretty low. However, if they are constructive, for example, in these red regions, they will be high luminescence. By the way, in these figures, it's the simulated forward luminescence with different thickness of active layer and different emission rule position. From these figures, it's very clearly shown that the different emission rule position is important for the LEC performance. Therefore, for my project, I focus on one of these topics. I want to investigate how does this current density will influence the emission rule position. In experiment, I make two types of devices. They are fabricated on glass substrate, and the ITO is the anode, aluminum is the cathode. In the active material, we use same emitter, super yellow, and same salt. For these two types LEC, the difference is ion transporter. One is 10 POH, the other is 10 POC. In 10 POH devices, the active layer thickness is 400 nanometer. In 10 POC device, it's 260 nanometer. The devices is characterized by this homemade Gaussian spectrometer. And this spectrometer, it can measure this algorithm spectra. For the devices, my project focuses on different current density. Therefore, we use we chose three different current density from 10 to 50 milliamp per centimeter square. And we also control the temperature for the devices during operation to a constant value. When we get this measured spectra from this Gaussian setup, we can fit in the measured and simulated spectra from samples. Then we get the measured emission rule position. Now I show my measurement data. First, we look through this 10 POH LEC results. Figure A, B, C, they plot this forward luminescence, voltage, and emission rule position. In this figure D, I chose this peak luminescence, and this figure E is a minimal voltage. Figure F, I plot this steady state emission rule potential. In the project, we define the steady state is where the voltage is at a minimum, like these three positions. We can see for this figure D and E, they perform as we expected. Like with the increase in current density, both the peak luminescence and the minimal voltage increase. The important observation for us is the emission rule potential. We can see with this current density increase, the emission rule potential, the value decrease. This decreased value means the potential moves towards anode. Then I mark this steady state emission rule potential in this simulated luminescence map. We can see when this current density increase, this luminescence gets smaller and smaller value. It means if we want to operate such devices, we don't want to use this high current density. So even it's a high current density, but after, for example, in this transient luminescence figures, we can see even it's a high current density, but after a few minutes, it gives this same luminescence and this low current density. So from this result, we have one observation about this steady state emission rule potential shift with different current density. The other one is it tell us for the high current density, it's not meaningful to operate a device. Now I move to the other type of LEC, it's TMP-OC LEC result. I plotted the same physical parameters. A, B, C, it's a transient luminescence voltage emission rule potential. And D, E, it's a peak luminescence minimal voltage. They are similar results. For this steady state emission rule potential, it also moves towards anode with increasing current density. Now I mark this emission rule potential in this simulated luminescence map. We can see even it's different current density, but they still sit in this red region, this high performance region. So for this TMP-OC device, it's all the current densities is fine to do this operation. After the result, we want to try to understand why there is this emission rule potential shift with different driving current. For this steady state emission rule potential, in these figures, we can see if this electron and the hole mobility, they are same, then the steady state emission rule potential will sit in the middle of the emission rule. But if the electron mobility is higher than the hole mobility, then the final steady state it will close to anode. Based on this theory, we think that the possible explanation for the emission rule potential shift is a different field-dependent mobility for the electron and the holes. In these schematic figures, like before this one, I plot like the electron trap and hole trap without electric field. If we operate some electric field, maybe this electron and the hole band, they will have a bending effect. When this electron traps, it decreases more than the hole traps. The final mobility between the electron and the hole mobility, it will increase with increasing current density. Then these values will cause an emission rule potential shift towards anode. In conclusion, based on this project, we have the important observation. The steady state emission rule potential will most in LEC with different current density. This observation can be one more guideline to optimize this LEC performance. For example, we can shift this emission rule potential by driving different current density. That's all. Thank you.